So let's go to this next one. So this one, we're not given a function definition, it's just r of t. And this one's in liters per second, and it wants us to set up with a starting volume of 0 liters at t equals 0, what is an expression that represents the volume of the balloon after 2 minutes in liters? So again, we're going to take the definite integral from 0 to 120, because the function is in seconds and it's asking about 2 minutes. And then we'll plug in our function. So since we're not given a function definition, I think that's just going to be the answer. They just wanted you to recognize the seconds and the 2 minutes and how to set it up. Once you're actually given a function, I'm sure they have, ways of doing that. But I'm pretty sure that's just what the answer is going to be. A lot of these exercises are just going to have you set up a certain equation. There's some partial fraction decomposition ones where you don't actually have to find A, B, C, or whatever. They just want you to set it up. So this is another example of that, where they just want you to set up the integral, but not actually solve for it. So let's go on to the next one then. Whoa, whoa, whoa. Okay, this one's a little off-center, but that's fine. So the temperature of a city t hours after 9 a.m. is modeled by the function t of t. According to the model, what is the temperature at 9 a.m.? So if t is hours after 9 a.m., then if it is 9 a.m., then t would equal 0 at 9 a.m. So then we just plug in 0 into this function. Sine of 0t over 12 is going to be sine of 0. 19 times sine of 0 plus 80. If you remember the unit circle, this is going to be like your 0, 0 point, the center of the graph. And you can think of these as like x and y coordinates. And with the unit circle, cosine is the x coordinate and y is the sine coordinate. So at an angle of 0, you'll have an x of 1 and a y of 0. So sine of 0 is 0, 19 times 0 is 0, plus 80. So the answer for part A is 80 degrees Fahrenheit. If you're not super familiar with the unit circle, haven't committed it to memory yet, I like drawing it out like that as an example. So now it's asking what the temperature is at 3 p.m. So if t is equal to 0 at 9 a.m., 3 hours later would be 12 p.m., and 3 hours after that is 3 p.m. So t equals 6 at 3 p.m. So now it's going to have you take the integral from 0 to 6 of 80 plus 19 sine pi t over 12 dt. And you can tackle this a few different ways. And the first thing that I'd do is split this into two parts. And I'd actually take the 19 out front from sine as well. So this might be easier because now you're just breaking it into two smaller integrals. You can do a u substitution here so that it's an easy integral of sine of u, which is negative cosine, and you'd multiply it by the 19. And then the integral of 80 with respect to t would just be 80t. So let's do that. If u is equal to pi over 12t, then du would be equal to pi over 12 dt, which means 12 over pi du equals dt. So I'm just going to focus on this right-hand one right now because the other one's easy. So I'm going to do 19 times 12 over pi, just bringing all the constants out front, evaluated from 6 to 0 of sine of u du. And that's going to be equal to, what is 19 times 12? 228. So we have 228, but it's going to be a negative, right, from cosine. 228 over pi cosine of u, evaluated from 6 to 0. To make this easier, I think I'm going to plug in these to get the u values. So right now they're at x, but I want them to be equal to u. This isn't required, but I just think it's easier to do it that way. So if we plug in 6 to our definition of u, well, I guess these are t, not x, then we'd get 6 pi over 12, which is pi over 2. If we plug in 0 to that, it's going to be 0. So cosine at pi over 2, if you remember that example I gave, where cosine is the x-coordinate, pi over 2 is right here, and this is 0, 1. So cosine at pi over 2 is going to be equal to 0. Then we're going to subtract a negative 228 pi, or over pi, and cosine at 0 is going to be 1, because it's the x-coordinate, times 1. So I think I'm running out of space here. Oh, I have a bunch on the right side. Here we go. So if you remember, we had that initial side of 80 dt plus, well, we just figured this out. We just figured out the right integral, which is a positive 228 over pi, because it's subtracting a negative. Then we can do this side. It's going to be 80t evaluated from 6 to 0 plus 228 over pi. 80 times 6 is 480. So this whole thing is equal to 480 plus 228 over pi. And that's going to be the temperature for B. Before I say that, I will check the answer and see if I got wrong along the way. So it looks like it's 80 plus 38 pi. Oh, just kidding. It's going to be 99. So it looks like whatever we're going to do for A, where it was just t of 0 is equal to 80, we'll do t of 6 is equal to 99. So it looks like C is the one where we're going to be integrating because it wants the average temperature over a period of 9 a.m. to 9 p.m. So I did B incorrectly, but I think it's still a great exercise. And you can double check if you have a calculator that does definite integrals or numerical integrals. This would be so for number C or letter C, it's going to ask what the average is. So the average formula for a integral is going to be this. (9 a.m. to 9 p.m. is 12. Because t of 0 is going to be at 9. Move 12 hours over, you get to 9 p.m. So this would be 1 over 12 minus 0, which is 12. And this is going to be integrating from 0 to 12 of 80 plus 19 sine pi t over 12. Since we had that happy little accident, we already know what this integral is. It's 80t minus 228 over pi cosine. I'll just plug in what our u substitution was. This will be evaluated from 0 to 12. So now we can just plug in 80 times 12 minus 228 over pi cosine of pi 12 over 12 minus 80 times 0 is 0 minus 228 cosine of 0 was 1. So 80 times 12 is 960. This is going to be pi. Pi 12 over 12 is pi. This is 0, this is pi over 2, this is pi. And the x-coordinate here is negative 1, 0. So cosine would be our negative 1 there. So if this is 228 over pi times negative 1, then we would subtract our negative 228 over pi. Let's see what they got for this one. It was like a 38 over pi. Okay. So it's going to be 960 minus a negative 228 minus a negative 228. So if we just rewrite that, it'd be 960 plus 228 over pi plus 228 over pi. So that'd be 456 over pi. Now we're finding the average, so we need to divide the whole thing by 12. And 960 divided by 12 is equal to 80. And 456 divided by 12 is 38. So this is our average temperature over the time period 9 a.m. to 9 p.m. And that looks like it's the same there. Let's look at one like number 8. How about that one? So number 8 is the integral of sine cubed x cosine x dx. So when you look at this equation, this integral, you have to determine what strategy you're going to use to integrate. I made the mistake of doing integration by parts with this one. That should always be, or it shouldn't be the first thing that you try. You should always see if you can do a u sub first, and then if you can't, then do an integration by parts. Because if you do a u sub here with u equal to sine of x, then du is equal to cosine x dx, and dx is equal to du over cosine. So when you plug in u, the cosines will cancel. And then you just have a simple integral of u cubed du. And then you'd plug u back in after you integrate. So it'd be like sine to the 4th over 4. So don't make the mistake that I did where you just try to integrate by parts. You might get the same answer, but it's not going to be as easy, especially with trig stuff. Sometimes two equations don't look like they're equal to each other, but they are. Let's look at number 10. Secant squared x tan to the 4th x dx. So again, you could do integration by parts if you so wish. That might be very difficult though. So I'm going to do u is equal to tan of x and du over secant squared x equals dx. So you can see when we plug in dx, these secants will cancel out and we'll just be left with u to the 4th du. And that'll be equal to tan to the 5th x over 5 plus c. So recognizing stuff like that is going to make your life easier. Sometimes if you see some odd or even powers with trig functions, you'll try to do the Pythagorean identities, but sometimes it's not necessary. Let's do number 19 here. This is going to be a trig substitution one. That was the integral of 1 over square root 9 minus x squared dx. So with these ones, I find it difficult to see what x is going to be equal to. If you remember the identity, cosine squared plus sine squared equals 1. You could have sine squared equals 1 minus cosine squared and have your x equal cosine. You could also have cosine squared equals 1 minus sine squared and have your x equal to sine. I'm not really sure which one is the right approach, but you just try one, and then if it gets you the answer, then it works. And you can try the other one if you'd like. So for this one, I'm going to do sine. And I'm going to recognize that this coefficient in front is a 9. So I'm going to make this a 3 because it's going to be squared, and 3 squared is equal to 9. So let's do 3 sine of theta, and then take the derivative of that, which is going to be 3 cosine theta, d theta. So plugging this into the equation, we're going to get 9 minus 9 sine squared theta times 3 cosine theta d theta. I'm going to take out a 9 from both of these terms. A 9 under the square root is going to be a 3, so I'm going to be left with a 3 out here. And then I'm left with 1 minus sine squared. I'm just going to put this stuff on top. We're left with that. So these 3's are going to cancel out. This is going to be our Pythagorean identity right here. So that's equal to cosine squared, right? So now I'm left with cosine on top. Cosine squared under a square root is just going to be cosine. So this whole thing is going to equal 1 d theta. The integral of that is just going to be theta. And now we'll have to do the substitution backwards. So if we set up this equation, divide 3 on both sides, we get x over 3 sine theta. Let's take the inverse sine of both sides. Inverse sine of sine just cancels out and gives us theta. So this whole equation is equal to the inverse sine of x over 3 plus c. Was that question 19? Yeah. Arc sine, sine -1, they mean the same thing. Let's look at 20 here now. 1 over x squared, square root of x squared plus 25. I don't know why this canvas is so jittery when I move it. It's going to be 1 over x squared, square root of x squared plus 25 dx. So we're going to look at the Pythagorean identities again. What's nice is if you remember this one, you're able to derive all other Pythagorean identities from it. So let's divide each term by cosine squared. This is an equal sign. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So here's your other identity that you're going to want to use. This tan squared plus 1 looks very similar to this x squared plus 25. So I'm going to have my x equal 5 tan theta. And I'm choosing 5 because I'm going to square it, and I want the number to equal that. So my dx is going to be equal to 5 secant squared theta d theta. Let's plug in x. We have our x squared out in front, so squaring our x is going to be 25 tan squared. Then we have the square root of 25 tan squared plus 25 times our dx, which is 5 secant squared d theta. So I'm going to take a 25 out of both of these terms. I'm going to be left with a 5 at the bottom. I'm just going to go ahead and multiply it with that 25 and get 125. Now we're left with this, multiplied by 5 secant squared theta d theta. You can see I shouldn't have multiplied it because the 5s are just going to cancel out. This is going to go back to 25. So now we're left with secant squared theta over tan squared theta. This is going to be our Pythagorean identity here. It's going to be secant squared over or under the square root sign, so it's just going to be 1 secant d theta. So I'm going to do some canceling out here, and now this is equal to secant on top over tan squared on bottom. Now looking at this, I don't immediately know what to do. So my first intuition is going to be to break them down to their simple parts. And when I do that, this is going to be equal to 1 over cosine times the reciprocal of the bottom, which is cosine squared over sine squared. So this whole thing would be equal to, the cosines cancel out, so it'd be cosine times 1 over sine squared. That doesn't really look very pretty either. It doesn't look like something that we recognize. So I'm going to say that that is not the approach that you should take. I'm missing a 25 out here as well.
Can't you replace that tan squared on the denominator with like secant squared plus 1?
Yes. Well, it wouldn't be secant squared plus 1, but it can be secant squared minus 1. Right. So if we move this minus 1 over, then we'd get secant squared minus 1 equals tan squared. Let's see if that helps us at all. My other thought was the power reducing formulas, but I would hope that they wouldn't spring that on us. So if we have secant theta over secant squared minus 1, where could we go from there?
If you cancel the secant theta on top and bottom, wouldn't it give you inverse?
Yeah, so if we have like a fraction like this is not going to be equal to 1 over x plus 1. You're unable to cancel this because this is like a combined term. It's its own thing. I'm going to say, I'm going to do what I did before where I broke this down into its parts, sine squared over cosine squared. And when we multiply this out, we'll get cosine over sine squared. So let's say you were just given this integral. I would do another substitution, right? Because cosine and sine have that unique relationship where when they're in an integral together, some of them can like cancel out. These shouldn't be u's, these should be thetas. So if I do u equals sine, then du would equal cosine d theta. There's a d theta here. So that could break it down to this cosine d theta is this part. So we'd have our du, and then our 1 over u is sine, so u squared. And that looks like something that we definitely can integrate normally. So if we do the integral of u to the negative 2, what are we going to do? We have to add 1, so that'd be u to the negative 1, and then we divide by this new power, which is negative 1. So it'd be negative 1 over u. So I'll just bring that in front. How much more room do I have? A little bit here. Okay, so if our integral now is negative 1 over 25u, u is on the bottom. Let's do the substitution back to sine. Firstly, sine of theta. Then we want to go back to our first point. So that would be theta equals the arctangent of x over 5, right? We divide 5 on both sides here, and then take the inverse trig function. And oh, I forgot to do this. This is always, I can't believe I forgot to do this. This is going to be like the most helpful thing when doing these trig substitutions, is rewriting the initial substitution you did, this part. So once we plugged in everything and then we took out the 25 and we did the Pythagorean identity, this all came down to be 5 secant. I can't believe I forgot to do that. This part is so important, especially if you're on the test or anything. You're going to want to write down this identity because it's going to be so useful when you try to plug it back in. Because you see this sine here, we don't actually have a definition for sine. All we have is secant and theta. So let's solve for secant there then. It's going to be x squared plus 25 over 5 equals secant theta. And, you know, I'm actually going to erase this part too. This is going to be x over 5 equals tan theta. And if you remember, tan theta over secant theta is equal to sine theta. Because if you break it apart, it'll be that. When the cosines cancel out, you're just left with the sine. So we just need to plug that in here. And that can get kind of messy because it's like a fraction within a fraction within a fraction. But if we break it up and do it in small parts, then it should be easy. I'm going to clear the screen here, but I'm going to need to write these down so I don't forget them. Okay. So we had x over 5 equals tan, and the square root of x squared plus 25 over 5 equals secant. And our entire integral measured out to negative 1 over 25 times 1 over sine. And sine is equal to tan over secant. So we'll just take x over 5 over square root x squared plus 25 over 5. And when we do that, these 5s will cancel out, and we'll be left with x over square root x squared plus 25. But that's going to be on the bottom. So since it's on the bottom of a fraction, I'm just going to flip it. It's the inverse of it. So then this would equal to negative 1 over 25 times the inverse of this fraction, which is x squared plus 25 over x. And that measures out to x squared plus 25 over 25x plus c. I don't know, I don't feel very confident in that answer, but we can definitely check. Negative x squared plus 25 over 25x plus c. Awesome. Yeah, we got there in the end. It was kind of shaky. Let's see if there's any more trig sub ones, because those ones can be kind of difficult to wrap your mind around sometimes. That's that. Oh no, I might be wrong here, but it looks like they only gave us 2. And then these are all evaluating definite integrals or doing estimations. You guys have the review in front of you. You can pick one that you'd like me to do. Otherwise, I'm just going to find another trig sub question online to walk us through.
I think I really need another trig substitution.
You said you really need one or you don't really need one?
I really need one.
Okay. Let's... I'm just pulling up a website for more practice problems. All right. So let's do square root of x squared plus 16 over x to the fourth dx. So again, we're going to recognize that this is going to be equal to that Pythagorean identity. So I'm going to have my x equal 4 tan, and dx is going to equal 4 secant squared. And I'm choosing 4 here because when I square it, it's going to say 16 tan squared plus 16, and that's going to look very similar to that. So plugging that in, going to get me 16 tan x, or tan theta squared, plus 16 over, what is 4 to the fourth? 256. So let's simplify this down. We're going to take a 16 out of both terms. It's under the square root, so that's going to become 4. And then tan squared plus 1 is equal to secant. That is also under the square root, so that's going to be equal to secant. And this is where I'm going to remember this step, where x squared plus 16 is equal to 4 secant. So it's always important to write that down so you don't have to go back and figure it out again. This is going to be over 256 tan to the fourth times 4 secant squared d theta. So these 4's are going to multiply to become 16. 16 over 256 is equal to 1/16. So I'm going to pull that out in the front. And then we're left with secant cubed over tan to the fourth. I'm going to do what we did last time and break this down into its parts. So secant cubed is equal to 1 over cosine cubed, and that's over tangent, which is sine over cosine. So that's going to be sine to the fourth over cosine to the fourth. This is equal to multiplying the top fraction by the reciprocal. So it's going to be cosine to the fourth over sine to the fourth. These are going to cancel out, and we're going to be left with cosine over sine to the fourth. So this whole thing is equal to 1 over 16 integral of cosine sine to the fourth d theta. And this problem looks very similar to the one we just did. So I'm going to have u equal sine, du is going to equal cosine d theta. So these cosines are going to cancel out, and we'll be left with 1 over 16, 1 over u to the fourth du. I'm running out of space here again. So I'm going to write down everything that is important for finishing this integral. And that's going to be x equals 4 tangent. That's also going to be this thing. Square root of x squared plus 16 equals 4 secant. And yeah, I think that's it. So that's clear. So we have 1 over 16, 1 over u to the fourth du. That's going to be equal to, it's going to be a negative because of this guy. So this guy is actually just u to the negative 4. And when we integrate, that's going to be u to the negative 3 over negative 3. It's going to be 3u cubed times 1 over 16. And 3 times 16 is 48. So this is equal to negative 1 over 48 u cubed plus c. But we're not done there. We need to plug it back in. So u is equal to sine, if you remember. I'm going to break apart this fraction so it's easier to understand. Whoops. So we're going to have sine cubed on the bottom. And if you remember, tangent over secant equals sine. Our tangent was x over 4. And our secant was square root of x squared plus 16 over 4. When we put these over top of each other, these 4's are going to cancel out. So we have sine equal to x over square root x squared plus 16. And sine cubed is going to be that whole quantity cubed. So now let's plug it into there. We're going to have negative 1 over 48 times 1 over x over square root x squared plus 16. This is cubed. So I mean, this is our answer, but I'm going to simplify it just because it looks kind of ugly right now. And trying to insert that into our that like online exam might screw you up. But it would suck if you got the answer right and you only got the question wrong because you didn't input it correctly. So let's simplify this just a little bit. When this is under the denominator, these terms are going to switch. It's going to be like the inverse of it. So this is going to be equal to square root x squared plus 16, quantity cubed, over x cubed. If you want to make this even easier, we can combine these fractions now. And I will write x squared plus 16 to the power of 3/2. The square root sign is a 1/2. And when you have an exponent to the power of another exponent, you can just multiply them. So 1/2 times 3 is 3/2. This is going to be over negative 48 times x cubed plus c. So that is the final answer for that question.
Do you have any tips of when to do u substitution or integration by parts?
I would just try u sub first, and you should be able to find out pretty quickly that you're running into a dead end. It's much easier to know or to recognize that u sub isn't going to work than recognize that integration by parts isn't going to work, because you might be like 3 layers deep in integration by parts before you realize, oh, this is going nowhere. But u sub, you should only be doing it like once, really, maybe twice. But you should, yeah, it should be much more apparent to you. So I would just always try to do u sub first. Like, I know it's going to be integration by parts if I see something like this. But if it's something like this, then I'm like, oh, I can take the u sub of x squared, you know. So that's how it can be complicated. Like, just these two terms have swapped places, and now your answer is going to be very different, and your approach is going to be very different. So. Do you guys feel pretty confident with the partial fraction decomposition part?
Can we do just one?
Sure.
Thanks.
I'm going to do this one. This one's just having you find the decomposition and not actually solving for it. So let's break apart. This is going to be a plus. If you have a root that's doubled, you're going to want to take the single part of it as well. And it's just a single term because x is to a single power. Same with this one, x is to a single power. It doesn't matter that it's squared. What we care about is the degree of the variable in the root. And then this one's going to be x squared plus 9x plus 45. And this is when you introduce this sort of thing. Because this top part is always going to be 1 degree lower than this bottom part, which is to the power of 2. So the decomposition of this one, you'd have one fraction with x to the x minus 4, one with x minus 4 squared, and then one with that whole polynomial. Was that sufficient, or did you want to do this one as well?
And would it be okay if we solve one out completely?
Yeah. So
Okay, thank you.
I'm going to find the roots of x squared plus 6x plus 9. This is going to be x plus 3 and x plus 3. So these two things are equal to each other. All I've done was kind of break apart that quadratic into its simpler parts. So now I can say this is equal to, or this fraction is going to be equal to some number a over x plus 3 squared plus some number b over x plus 3. So again, with these double powers, a repeated root, we're going to do it once with the power, and we're going to do it a second time without the power. So now I'm going to write the original fraction, which is 3x over x plus 3 squared, equals a over x plus 3 squared plus b over x plus 3. So I'm going to multiply this side by x plus 3 squared so that that cancels out, and I'm only left with 3x. But whatever I do to this side of the equation, I need to do to this side of the equation. So this is going to cancel out with this, and we'll be left with a. This is going to cancel out once, and then we're left with a x plus 3. So now I'm going to multiply this out, and we're going to be left with bx plus 3b plus a. So these things have to be equal to each other. That's what we've found out. So from this, you can easily tell that b is going to be equal to 3. So b equals 3. And now we need to solve for a. So this part is going to be your x part, and this part is going to be your constant. And the constant here is going to be 0, right? You can imagine an imaginary number sitting there. So that means that 3b plus a has to equal 0. So if we plug in that, it's going to be 9 plus a equals 0. A equals -9. So now we figured out what a and b are equal to. So we can rewrite this integral as 3x plus 3, right? That's this part, dx, minus 9 over x plus 3 squared dx. So I just broke apart this fraction because this is going to be a -9, this is going to be a 3. So I wrote the 3 first, and then this is the -9. So let's simplify this further. It's going to be 1 over x plus 3 minus 9 x plus 3 squared. So this first part is going to be the natural log 3 times the natural log of x plus 3 minus 9 So for me, I don't initially know what this is going to be, so I would do like a u sub, and then it'd be 1 over u squared. And the integral of that is equal to 1, negative 1 over u. So then this would be times negative 1 over x plus 3. So if we simplify, that's going to be x plus 3, 3 times the natural log of x plus 3, plus 9 over x plus 3, plus c. We're going to consult the answer book and see if we got it right. That was number 27. So there we go. And what about, how do you guys feel about these estimations of definite integrals with the trapezoid, Simpsons, midpoint, left, right? Does that make sense to you guys? Before we go there, it looks like B sent a message in chat, so I'm going to help them with that before I move on. So this is kind of pertaining to what the other person asked. If you have the integral x sine of x dx, are you going to use u sub or integration by parts? So for me, I would integrate by parts and have u equal to x and du equals dx. Right? This is just a first degree term, so that'll be really easy. And I know that it'll only take one time. So then dv would be equal to sine dx, and v would be equal to negative cosine. Then we'd have negative x times cosine minus the integral of negative cosine dx. That's equal to negative x cosine x plus sine. So if you tried to do like a u sub, I don't know what you would do, like u equals x, then you'd just be left with the same problem. But so that's the first one. Then let's look at this second one. Whoa. This is x to the fourth over 1 plus x to the fifth dx. So would you use u sub or integration by parts? Well, if I tried to integrate by parts, then my parts would be this, and 1 plus x to the 5th to the negative 1. I don't know about you, but that seems pretty difficult. I don't know. Taking the integral of that, or not integral, we'd take the derivative of that, which would be like that or something. I don't know, chain rule. But then we have to integrate this later, so that seems too difficult. So I would have u equals 1 plus x to the 5th, and du equals 5x to the 4th dx. Well, this part is just this part. So I'd say u sub for that one. Much easier to do it that way. Oops. Let's see what else they have. It's going to be x to the 4th e x to the 5th dx. So you're going to use u sub or integration by parts. I would heavily recommend u sub in this one. That is all. Let's say if you did have like this, like I wouldn't even know what to do for this equation, because if I have to take the integral of it, I would think to u substitute that. But so that's kind of my general approach, is if you're running into a wall right away, then it's probably not going to go over well. The next example is this. You can see how similar it is to the other one, where if you recognize the parts that are being used, then you can do an easy u substitution. And then lastly, it looks like square root 8x plus 1 dx. If we did do integration by parts, it'd be 1 times this. Or this would just all be to the negative 1/2. So I don't know. I would just definitely do a u sub here of 8x plus 1 du equals 8. And then you can just do this. So I would just always give it a try with both of them. Just set up the variables, and then if it looks like something you've never seen before, or it looks incredibly difficult, then you're probably barking up the wrong tree. So I always try u sub first, because you can find if you're doing it incorrectly. Yeah, hopefully that answered some of your questions about that. Do we have any more questions, or I could go over the estimation of definite integrals? Cody, you're welcome. I cannot hear you, but I can definitely post this video I've been recording, but I don't know how useful this video is going to be. You'd probably be better off watching like higher production quality videos that I've linked in the notes or even class resources. But I think I'm going to end it here unless anybody asks a question in the next 5 or so minutes. I'm going to run to the bathroom. Oh. All right, I'm going to stop the recording now.